In bromination of an alkene, the bromine approaches, it becomes polarized, it forms a carbocation in equilibrium with a bromonium ion, and that carbocation doesn't lose a proton to give a substitution product, but instead it reacts with bromide to give an addition product. Unlike bromination of alkenes, bromination of benzene doesn't happen unless a Lewis acid is present. Let's imagine one is there to activate bromine by polarization. Then benzene attacks the bromine in a slow step, which is slow because the aromaticity of the benzene is lost. Some students tend to forget that one of the carbons now is sp3 hybridized, and the other one, the one with the positive charge, is sp2. Loss of a proton from the sp3 hybridized carbon gives back the aromaticity to give a substitution product. Bromide does not add to the positive charge to give an addition product. Bromination of alkenes and bromination of benzene and arenes is fundamentally different. In general, the key concept to remember is electrophilic attack on an arene is slow. It gives an sp3 hybridized carbon. That loses a proton to regenerate the aromaticity in a fast step to give a substitution product. If you understand that, the rest of the chapter is easy. What could that electrophile be? Well, it could be Br plus in a bromination, nitronium, that's NO2 plus in a nitration. It could be a deuteron. It could be methyl plus in a methylation, or it could be SO3H plus in a sulfonation. And when the proton is lost, we get chlorine substitution products, nitro substitution products, methyl substitution products, and sulfonic acid substitution products. All the same concept. Iodinations happen in the same way. Acylations can happen in the same way to give ketones. And nitrosylations can happen in the same way. Of course, it's useful to understand the chemistry of how these electrophiles are formed. And for that, it's necessary to draw out the corresponding acids. So protonation of nitric acid, it sounds unlikely, but it can be done, gives a nitronium ion after loss of water. Protonation of nitrous acid gives a nitrosonium ion. Protonation of sulfuric acid gives a sulfonium ion. And in halogenations, a Lewis acid is necessary. For chlorinations, it's nice to have a chloride, like aluminum trichloride. For brominations, iron 3 bromide. And for acylations, using acid chlorides, tin 4 chloride would be a good choice. And for alkylations, tin 4 chloride could be used also, but why not use boron trichloride? All Lewis acids capable of extracting a halide from a halogen. The following examples just fill in the reagents. So nitration is done with sulfuric acid and nitric acid, iodination, methylation, or benzoylation. The reactions will go slower if there's an electron withdrawing group on the benzene, and faster if there's an electron donating group. Regioselectivity of electrophilic attack is interesting. So if we have a monosubstituted benzene, will it afford the 1,2, 1,3, or 1,4? That's the ortho, meta, or para substitution product. The answer can be seen by viewing the carbocation intermediates. If resonance forms of that carbocation can place the positive charge next to the X group, and the X has a lone pair to donate, then there's an extra canonical form. That occurs in ortho substitution, but it doesn't occur in meta substitution. And it does occur again in para substitution. So ortho and para substitution is favored if the X group can donate lone pairs.